So what we're doing in F5 is we're looking at finding the area between two separate curves. We're going to start off with an example that we could solve geometrically. We can do it. We can get the answer without using calculus. So we're going to kind of do one of these examples where we get the same answer two separate ways. We'll do it kind of by hand, and then we'll do it just showing it with the calculus. So I have probably the simplest situation I could come up with that is the area between two curves. I have a horizontal line at the top and a diagonal line at the bottom. I have the equations for them. The horizontal line is the line y equals 5, and the diagonal line is the line y equals 1/2 x. There are a couple ways that you could find the area that's shaded. One way would be to split it up into a triangle and a rectangle, but that's not the way we're going to do it, mostly because it doesn't match what we do with the calculus. So I just want to say that, yeah, one thing I could do here is find the area by finding the area of that rectangle and that triangle. But to match the way we're going to do it with calculus is we're going to find the area of this rectangle and then subtract away the part that isn't shaded. So we're going to take the orange's area and subtract the whites, right? Well, maybe we have now talked about 3 different ways to find this area. The way that I said we're not going to do, the way that we're about to do, and then the calculus. So what is the area of the orange rectangle? 30, right? So the orange rectangle is 30. What's the area of the white triangle? 9, because it is 6 by 3. So 1/2 6 times 3, which is 9. So that means the area of the shaded region is 21. Yep. Oh. So yeah. Had we done it the first way, we just would have done 12 plus 9, because the white triangle would be the same as the shaded triangle, how I had it drawn before. Same result. When we do the calculus, we're going to get the same result. 3 ways to do the different problem. Just, yeah, even another way to do it. So what we're going to do is we're going to do what we just did, but we're going to do it with calculus. The area of the rectangle is the integral from 0 to 6 of the function, which is 5 dx. And then subtract away the area of the triangle, which is the integral from 0 to 6 of 1/2 x dx. So 2 separate calculus problems. Find the area underneath the horizontal line. That's our first integral. Find the area under the diagonal line. That's the second integral. Take away the part that isn't shaded, and you'll have the area of the shaded region. So we end up with 5x evaluated from 0 to 6 minus 1/4 x squared. Yeah, I was about to cancel the 2's like a goof. Yeah, 1/4 x squared, but I was realizing that was going to give me way too big of a number. Yep, from 0 to 6. And plugging the zeros in those is going to give me 0. My 5 looks like a tiny integral symbol, and it's confusing me. There we go. Yep. 30 minus 0, of course, minus 36/4 minus 0, which is our 30 minus 9. Exact same thing. Boom. Yep. So one of these problems is as complicated as the person who makes it who's making it up wants it to be. There actually are 3 separate sections, I think, of this in the AP syllabus. I'm remembering correctly. They're right here. Yeah, this represents 3 sections. So we are going to kind of look at a couple different things. The key to setting this integral up is you need to have the larger function first and the smaller function second. And by larger and smaller, I mean area-wise. But the higher up function is always going to give you more area. So one of the parts of these problems is figuring out which curve is higher and which one is lower. If one curve is always higher and the other curve is always lower, you can kind of do it with just one set of integrals. Or I should say one set of limits. But when they start intersecting, those are going to be the more complicated problems. So basically a formula similar to what you have on the board, but kind of only for this case that we're looking at right here. The area between two curves is just the integral of the two curves subtracted between the bounds, as long as your first curve is larger. So it's higher up on the graph. So all I have to do is subtract the two curves as the integrand and integrate from where they need to be. One of the things that happens, though, too, with these problems is when the curves do intersect, a lot of times that creates natural spots to integrate from. So if you have two curves that intersect, we're going to see when we sketch this out in a minute, it will just say to find the area between the two functions, and it will be our job to find those intersections as well. So let's take a look at these. I'll kind of do a sketch. You guys can do it with me. We'll talk about what these curves look like, and that should hopefully solidify what I was just saying there. So we have two functions, 2 minus x squared and g of x equals x. What does 2 minus x squared look like? Yeah, so negative x squared, you're right, its vertex is going to be at 0, 2, which is a downward parabola. So we've got a downward parabola, and we've got the function y equals x, which is just diagonal line, correct? Yeah. So our function looks something like this. And what this question is asking us to do is find the area that's kind of bounded between the two of them, which would be this. But we have to find those intersection points. And the way you do that is you just set the two things equal to each other. We just say that 2 minus x squared equals x, which is quadratic, so we should bring everything to one side. So bringing everything to the right gives us x squared plus x minus 2, which is x plus 2x minus 1, which is an x value of negative 2 and positive 1. So I know that this lower point has an x value of negative 2. This upper point has a x value of positive 1. What's the y value? You can just plug it into either. And which one's the easier one to plug into? Yep. Yeah, plug it into this one. Every point on that line has matching x and y values. So if it's negative 2, it's negative 2. And if it's 1, it's 1. You actually don't even need those y values, I believe, to solve the problem. Because now we found those intersections to figure out where to integrate. We are going to integrate from x equals negative 2 to x equals negative 1. Our higher function is the 2 minus x squared, and our lower function is the x. Yeah. Nope, yeah, positive 1, thank you. All right. I feel like this is an algebra thing we've seen a million times, but if g of x had like two terms to it, if that was x plus 3 or x plus 4 or something like that, you would need to put it in parentheses here and then distribute that x in, right? That's how algebra works, so keep that in mind. If you just put a minus and then you stick a multi-term thing there, you're going to end up with the problem wrong. Okay, so I know how to figure that out. You know how to figure that out. Figure that out. What is that area? Yeah, sure thing. How many mistakes have I made? Three. All right. 2 minus -4. Yep. Minus. I did it term by term rather than 1, 2, 3 minus 1, 2, 3. That kept my thirds together. So I plugged 1 and 2 into 2x. I plugged 1 and 2. No, I'm saying 2, but I mean -2 into x cubed over 3. And I plugged those into x squared over 2. Kept my minus signs. Plugging the 1 gave me a positive. Minus -2 cubed is -8. -2 squared is +4. I think I did good. All right, nice, cool. I thought for sure I had made a mistake somewhere along the line there. Yep. Yeah. So you really do have two options to do this. You could have written 2 minus a third minus a half minus the quantity, -4 plus -8 thirds plus 4 halves, or plus 4 halves, and would have also came out. But that is one strategy to do when you've got multiple terms to do. Just do them term by term. Top minus bottom, top minus bottom, top minus bottom. I think that keeps your work a little bit more organized, and I managed to not make a mistake, so I'll take that as a win. Okay. Hey, calculator active. And feel free to pop your Chromebook out and play along. Sometimes it works and sometimes it doesn't. It's weird. Y equals x squared. Y equals sine. This is a terrible example. There is no area between the curves. Make it sine of x squared plus 1 or something. Make it x squared minus 1. Why not? Hey, there we go. So just change the problem so it's x squared minus 1, so you actually do get some bounded area there. Obviously, we're talking about this space in between the red and the blue. And really it is. These are pretty quick and easy because it's just a matter of finding the bounds. Since both of these are kind of have y-axis symmetry, those bounds are the same numbers, just 1 plus, 1 minus. It's just a matter of clicking on them to get the number. Use as many digits as possible. Not sure if the AP, I think you might, I don't know if you have that button on the AP version of the Desmos calculator, but it's just a matter of doing the integral from negative 1.39089 to positive 1.939089. And if I was smart and had actually labeled these as f of x and g of x, I'd be good. Because I can just type those in that way. G of x. Boom. But this time I did the way I just did f and g. So it does look like g is the higher function. So I need to type g of x minus f of x. It's probably going to yell at me because it wanted me to put that in parentheses. It is. And there's our answer. One thing that you'll notice, or it should make sense to you when you do these, if you get a negative answer for one of these, you are wrong. Because the question is always, what's the area between the curve? So we are asking a question that can only have a positive answer. I want to know how much space is in here. I'm asking about an actual just area, like a practical area, not so much a signed area like we do when we say like area under a single curve where you could get a negative. So you should never get a negative answer for your areas under a curve. If you're in one of the situations that we've seen so far, so there are there's only two intersections. There's not an intersection in the middle. If you've just got one simple space carved out and you put the functions in backwards, this will just be the negative version of it. Now, if these things intersect multiple times, this is going to be completely wrong. But in these ones, if you just happen to put f of g of x minus in backwards, you're just going to get the negative version of it. So, if you're looking at the picture and you realize that, you're pretty good on that one. So we end up with, fill out our paper, this one, 1.39 of, what was our higher function? Sine of x squared, right? And there you can see I put my parentheses in there. And our answer was 2.356. So yeah, so I mean, man, Desmos and a question like this that's calculator active, life is super easy. I don't feel like these end up too often to be calculator active in the open-ended, but I'm sure there's MCQs, sorry, FRQs, but I'm sure there's MCQs that may be like that. So, okay. So another thing that we can do, and we're going to look at this, and I think this is our last example for today. Yeah. Actually, we'll do 5 too. We'll do 4 and 5. Another thing that we can do here is we are not restricted to finding the area by butting up against the y-axis. We can actually find area with respect to the x-axis as well. So we'll kind of look at this in example 4. We're going to do example 4 two different ways. We'll do it the way we've just been doing it, and then we will do it, but we'll measure our area up into the x-axis, and we'll find that it's actually a simpler integral to do it up against the x-axis. So example 4 makes things a little bit more complicated the way we've been looking at it, because our bottom of our function is kind of piecewise. From 0 to 6, the bottom of our area is just the line y equals 0. I didn't want to say the right letter there. But then we switch to the line y equals x minus 6. So we actually have to integrate in two parts here. We've got to integrate from 0 to 6. Our upper function is the square root of x minus our lower function, which we're just integrating up until the x-axis. That lower function is 0, which, man, I could have just integrated the square root of x. So up from 0 to 6, it's just the regular thing we do with the integral. Find the area under the curve to the x-axis. But then I've got to add the remaining area, which is the integral from 6 to 9 of the square root of x minus our second function, which is x minus 6 dx. There's some things we could do here. In the end, we're going to have to plug 6 into the square root of x's antiderivative twice. They're just going to kind of cancel out. There are some integral rules we could do here, but I'm just going to kind of go to town with this one as written. What's an antiderivative for the square root of x? Nope. That's over square root of x.
2, yeah.
Yep, 2/3 x to the 3 halves. The minus 0 doesn't do anything, so we'll evaluate that from 0 to 6. And then we've got to do the second integral, which is going to be same thing. So 2/3 x to the 3/2. Make sure you don't forget to distribute in. So that's going to be minus x squared over 2 plus 6x. And we've got to evaluate that all from 6 to 9. So ready, go, evaluate that. Don't bother with it because you are going to get it in that first integral, and then you're going to get the exact same thing in the second integral, and they're going to have different signs. So you don't need to do anything. You don't need to write, when you evaluate here, you don't need to write anything other than 6 to the 3/2 power. I don't know. Do the math and see why yourself. No, don't say those words. I just got done saying you won't need to write anything other than 6 to the 3/2 power here because you're going to be writing it twice and they're going to end up having different signs. So they're going to cancel out. When you write it here, you'll be plugging it in as an upper limit. You'll have 2/3 6 to the 3/2 power. When you write it here, you'll be plugging it in as a lower limit, which means you'll have minus, because it's a lower limit, 2/3 6 to the 3/2 power. And whatever number that is, it's going to be the same here and here and cancel out. Waiting for the spoilers.
Okay, I have to certain one.
$80 minus 35, 45. Okay, I believe that's the answer. I can see 13 squares in there. Yeah. The mental math that I did along the way to make my life easier were obviously canceling those two things out. This is a positive 2/3, 6 to the 3 halves. And Jack, you see why this is a negative 2/3, 6 to the 3 halves? That was the best sound in the world for me. I did not do 3 to the 3rd power. I did not multiply 3 times itself 3 times and then divide it by 3 because one of those things canceled each other out. So I looked at this as 3 squared times 2. That's how I got my 18. When I had to do 81 minus 36 into my head, I said those are both multiples of 9. So my answer had better be a multiple of 9. That helped me figure out 45. And the same thing here. This was 54 minus 36. So I knew the math was going to come out to a multiple of 9. So I'm like, okay, if I had 20, is that right? Is 54 minus 36 27? Or did I mess that up? That's wrong, right? Oh, that's only 18. Oh, it is. I'm just pointing to the wrong spot. Yeah, gotcha. Yeah, so I'm like 20 makes 56, so got to be 18. Anyway, yeah, I was just pointing to the wrong thing there. So I said there's an easier way. Let's take a look at the easier way. We can integrate against the y-axis. We can also integrate against the x-axis, but that means we need to kind of shift our entire perspective. We need to think of this not as a function of y equals a function of x. We need on them to be x equals a function of y. Our higher function is going to be further to the right. Our lower function will be further to the left. So just a total shift in perspective, which means we need to take our two y equals equations and make them x equals equations. That's easy. Instead of y equals x, square both sides, I get x equals y squared. And instead of y equals x minus 6, I get x equals y plus 6. My limits are going to be x values because I'm going to be, or sorry, my limits are going to be y values because in the end, that's what variable I'm going to be plugging into. So in this time, I'm going to integrate from 0 to 3. My upper function is y plus 6. And my lower function, again, we're thinking right or left when I'm saying upper and lower, is y squared. dy. Yeah. So yeah, so everything's changing when you sort of shift perspectives here. Your limits, if you're ever not asking yourself, wait, I don't remember which one goes where, these are y values that I'm integrating on, so I need to plug y values in for y. If I do things like plug 0 and 6 in, plugging x values in for y, there's never a world where that's correct. So, yeah, let's do it. This should be a lot easier. We should end up with y squared over 2 plus 6y minus y cubed over 3. But this time we're evaluating from 0 to 3. And all of the zeros will go away. So we end up with 9 halves plus 18 minus 3 times 3 times 3, but divided by 3 is just 9, which is 9 plus 9 halves, which is 18 plus 9 halves, which is 27 halves. Well, that was easier.
Nice.
Yeah. Mm-hmm. No need to raise 6 to the 3 halves power. Okay. All right. So yeah, I think that's a good place to stop for today. I'll let you guys practice some of this.